Kavi, can you hear me?
Yes, Doctor, I can hear you.
Alright, okay. Thank you, Doctor. Okay, to show respect and as a sign to our appreciation to the speaker, please mute your microphone during the session. Thank you. Alright, our speaker, ladies and gentlemen, it is my pleasure to be here as moderator for this sharing session. My name is Dr. Nik Norziehana Che Isa from Center of Foundation Studies, UiTM Dengkil, member of EMaS Group. Okay, on behalf of the organizing committee, we wish to extend our warm welcome to all to stay motivated weekly sharing session with 5-star UiTM Research Group and Research Initiative Group Webinar Series 4.0 2022 organized by Research Nexus UiTM, Office of Deputy Vice-Chancellor Research and Innovation. Ladies and gentlemen, our speaker for this session is Dr. Kavirajaa Pandian, which is member of as Electrochemical Materials and Sensor, EMaS RG UiTM. Dr. Kavi is a senior lecturer from UiTM Cawangan Negeri Sembilan, campus Kuala Pilah. Dr. Kavi is an alumni of Universiti Malaya, where he graduated in 2015. Dr. Kavi research interests include conducting polymers and chemical sensors. Dr. Kavi has been active in various research activities by securing both internal and international grants, such as Grant Penyelidikan Lestari SDG Triangle and RSC Research Fund from Royal Society of Chemistry UK. He has published more than 20 index articles up to date. On his journey on the administrative part, Dr. Kavi is serving as the chief editor for Journal of Academia under UiTM Negeri Sembilan and serving as the section editor for Scientific Research Journal under UiTM Perlis. He has served as the head of publication bureau in several national and international conferences, and he has been an active speaker in research-related matters within the campus and faculty level. He also has been invited as peer reviewer about 60 times by Scopus and WOS Index journals. Dr. Kavi also has received several awards that includes Anugerah Perkhidmatan Cemerlang, Anugerah Akademik UiTM Negeri Sembilan, and Anugerah Apresiasi Rektor UiTM Negeri Sembilan as prolific writer and national level collaborations. Alright, so without further ado, I would like to invite our speaker. Please welcome Dr. Kavirajaa with his title, Integration of Waste Fillers into Polyaniline for the Development of Chemical Sensors. The microphone is yours, Dr. Kavi. Welcome.
Thank you, Dr. Nik. You can hear me, right?
Yeah, sure.
All right. So first of all, thank you to Renew for having me over here to share a little bit of my research experiences on the given topic over here. So I joined UiTM. A little bit about myself. I try to make it a very quick one. So I joined UiTM. I completed my PhD in 2015, and then I joined UiTM in December 2015. So 2015 is such a short period for me in UiTM, and then in 2016, I was still, getting familiar with the academic system and so on. So I haven't fully started my research yet. Only in 2017 I started on the selected project topics over here. So when I start my research, I wanted to set a long distance goals. So when during my PhD, I was trained to synthesize this conducting polymer known as polyaniline, and also I developed the chemical sensor by using this polyaniline. So I don't want to deviate too much, but at the same time, I thought of mix another material so that making it as simple as possible. Because when I started with without any funding, and also most of the results that I'm going to share today is based on my FYP projects. So in that sense, in 2017, when I started, I said that I wanted to set some goals, right? So I thought probably I can look towards this waste to wealth aspect, because I think we are generating lots of waste. So probably we can look into how we can recycle. But then waste to wealth is something like a very general term that it's like does not fix with any policies or anything. So that's why I looked further, and then I realized that probably in the Sustainable Development Goal number 12, there is a item called responsible consumption and production, which also cater for these waste to wealth, where how we can recycle or upcycle certain materials. So I set my goals towards these two directions, waste to wealth and also the SDG number 12. From there, I started off with a topic, integration of waste fillers into polyaniline for the development of chemical sensors. So I belongs to the EMaS group as one of the member, and also belongs to another special interest group under my campus, which is Advanced Material for Environmental Remediation, AMER. So I'm from campus Kolapila. So for today's sharing session, my outline is going to be a brief introduction about the waste generation, and then something about this polyaniline, what is this conducting polymer, how it behave, and so on. And then the third part will be on the polyaniline shells-based composite sensor, very simple sensor that we have constructed in our lab. And then the fourth section might be on the polyaniline by using chitin or chitosan-based material, and then other waste-related projects that we have ongoing in our lab. So yeah, so as I mentioned earlier, I started the research somewhere in 2017. So in 2016, while doing some reviews and so on, I found a report on the Malaysian waste management, which states that out of 38,000 waste that is being produced in Malaysia, 15,000 tons of waste are food waste. And then another report stated that we are actually producing about 30,000 tons of waste, because two different studies, that's why their values are different. Only 5% are being recycled. So what happens to the 95% of the waste that's outside? It might be just discarded at the landfills. So let's get back to the landfill later. And during the same year, somewhere in 2016, 2017, maybe I got to know during that time period, where the shell out activity, it's a social activity which gets familiar. We will spread a thin sheet, and then we will be served with various types of seafoods. And then I started to wonder what happens to these seafood shells. So they will be just deposited at the landfill, right? So why not I can collect, and then I can try to think of doing something. And also I started to think like what happens to the future of these shells once it deposited at the landfill. What happens? So it's going to be piled up just like this, which will bring more burden to the environment. Apart from that, we know that these shells are biodegradable materials, so it shouldn't be a problem. It's not a big problem like plastics waste and so on. But still, biodegradable, when it degrades, it's going to produce some kind of a pungent smell. So when I read further, the pungent smell is due to the ammonia gas, all right? So if let's say we are exposed, if let's say our housing areas and so on, like we are located nearby these landfill areas and so on, this ammonia gas, if let's say we are exposed to this ammonia gas on a constant phase, because the threshold value for ammonia is 25 ppm. So this is the threshold value. If let's say we are exposed to this value above this value for a longer period of time, definitely it has some health effects such as like temporary blindness. It can cause injuries to the mucous membrane, and also some irritation to the eyes and skin. All right, so these are the problems that comes from this biodegradation of these waste shells. So I thought probably I can start to investigate what is the potential that these shells contain. So my very first study, I didn't start with the seafood shells. I started with the chicken egg shells, because that's much more easier to collect even from my house itself. I can easily collect. So I just wanted to go as low cost as possible. So that was our ultimate aim, because of lack of funding. So when we look at these shells, generally they contain high percentage of calcium carbonates, and some studies shows that it shows a better mechanical properties when integrated with some polymers as fillers, and also it can improve the lifespan. But in terms of lifespan, in throughout our work, there are some works that it improves the lifespan, but there are some works like, we don't see a proper improvement in terms of the shelf life of the sensor itself, right? So, yeah, so I got to know that, okay, it contains a higher amount of calcium carbonate. And normally when I read the literatures, they all normally use the commercial grade calcium carbonate, which you go through a strict protocol and so on. So I thought, why not just collect, we grind it, and then probably we can just make it as a filler with the polyaniline. So that was the initial idea. So now let me talk a little bit about this conducting polymer. So the second part already. So maybe many of you out there also expertise in this polyaniline. So we have like more than 30 types of, sorry, 25 types of conducting polymers out there. So among them, polyaniline seems to be one of the attractive conducting polymer because of their different oxidation states. Where one synthesize, when you just take these chemicals and then you put inside the beaker and then you just cook it like how we do in the kitchen, right? So you will end up getting the emeraldine salt. Okay, so this is the first name that you will be seeing because it will be in the green color. That's why I put in the color labels as well over here. So very simple chemistry about this emeraldine salt or this polyconducting polyaniline is that when we let it to react with any types of base, it will be converted into emeraldine base, which will look blue in color. And then immediately we can revert it back to the green color emeraldine salt by letting it to react with an acid. Okay, so normally we use hydrochloric acid, or we can also use weak acids. Okay, but definitely weak acids will take some time to reprotonate, I mean to redope this emeraldine salt. On top of that, we also can fully reduce. This is the fully reduced part. If let's say we fully reduce this emeraldine salt, it will go into a pale yellow or colorless type of the appearance of the material, which is licomaraldine, which is known as licomaraldine. So my PhD work was focused on this aspect, which is emeraldine salt and licomaraldine. But then it involves some tedious work. So when I started my research over here, I don't focus on the licomaraldine part, fully reduced part. I just focus on this very simple acid-base chemistry. And on the other side, we also can make it fully oxidized. When we fully oxidize it, it is known as pernigraline, and it will be kind of purplish color. Okay, now. Okay. Right. So if we look at these four different structures of polyaniline, only emerald salt has these polarons. We call these as polarons. Okay, and also we can see the conjugation appears compared to this structure or this structure or this structure. So this pernigraline, licomaraldine or emeraldine base, these structures might have conductivity, but it might be very low or maybe no conductivity at all. But emeraldine salt will have certain degree of conductivity, and this conductivity depends on how we prepare, how pure it is, and so on. So this work about the conducting polymers, the very first conducting polymer was the polyacetylene actually, which was discovered in 1970s. That was an accidental discovery. And many works has gone through since then. And then this trio, Alan McDiarmid, Hideki Shirakawa, and Alan Heger. So this trio got the Nobel Prize in the year 2000. So we can assume that conducting polymers got three fathers. But out of the three fathers, I think we only have one living legend now, which is Prof. Alan Heger. The other two already passed away. So this is the basics of the polyaniline. Okay, next, let's look into the methods, how we prepare and how we did the overall sensor measurements. So first we collect these shells from the restaurants or sometimes from our stores and so on. We will wash it and we will try to remove the membrane layer because like shells will have certain membrane. We don't want to include the membrane because the membrane contains protein and there might be so many disturbances then because there are many studies out there which just focus on this membrane alone. So we don't want that membrane to disturb our overall performance. So we remove those membranes just by boiling and then washing it cleanly. And then we will grind it. We'll sieve. Why we are sieving? Because even though we grind it, but due to the blade size and so on, we don't really get fine particles. So we wanted to use very fine particles. The reason is later I'll explain why. Okay. Then we have used several types of shell-based powder, like CES is a chicken eggshell, CS is a crab shell, QES is a telur burung puyuh quail eggshells. And then we divided it into a different ratios like 20, 40, 60 milligrams so that we can make the composite material. So here we sieved, and then our motive is to get very fine particles, like few micron size only, because we wanted to do ex situ polymerization. We are not doing in situ because in situ the process will be tedious a bit. So we need more time to perform the washing process and so on. I will explain that in detail over here. So this is the synthesis and preparation of penny and also shells-based films steps. So the standard protocol of producing this conducting polyaniline is we have to disperse first aniline monomer. Before we disperse, we have to make sure it's doubly distilled. And then we have to disperse by using one molarity. One molarity is enough. We don't need to use a high concentrated acid also. Then we have to add it with an oxidant, which is APS solution. So APS solution, it can be, APS is a solid form, so it can be dissolved either with hydrochloric acid or maybe water. It depends. In this case, we use hydrochloric acid because we wanted to maintain the same environment. And then it will be pre-cooled as well. And then we will add it. So here, one of the steps that I think I didn't show is we use polystyrene box and then we fill up with ice cubes over here overnight. We wanted to make sure 0 to 5 degrees Celsius. Okay, the constant here is almost, I think, almost any polymerization are exothermic polymerizations. So exothermic means it's going to release heat. On top of that, when APS, oxidant, is added over here, it will release extra additional heat energy as well. For this conducting polymer, polyaniline, typically for the polyaniline, the heat is not really preferred because during my PhD, I've done comparison between room temperature and also 0 degrees Celsius. Room temperature, the conductivity, their conjugation, everything is like out of order because of elevated temperature. So we don't want the elevated temperature. That's why we will do the polymerization at a very low temperature, which is 0 to 5 degrees Celsius. Okay, and then we will do a normal process, which is filter and wash. And then here, so this step over here, okay, after we filter and then we wash it, we will collect the precipitate. Once we collect the precipitate, we let it to immerse inside the ammonium hydroxide. Ammonium hydroxide is a base. Okay, the reason why we are using ammonium hydroxide over here is to dedope. Dedope means something like, I have to go back here. Okay, all right. So this is doped state. This is de-doped state. So if let's say we are going back here, I mean, sorry, from initially we will get doped state, but then we are going back to the de-dope, and then we will do a re-doping. We are doing re-doping. Okay. The reason for that step is basically because when the polyaniline produced, which is green color, it might not have uniform polarons or maybe dopants throughout the polymer backbone. So when we de-dope by using ammonium hydroxide, we will let it to immerse for 24 hours as well, and then we will get a blue color solution. So we will filter it. Okay, this one we will filter, and then only we will add toluene as a solvent and DBSA, but toluene is toxic, so nowadays we are no more using toluene already. We use the DBSA, dodecyl benzoate sulfonic acid, which is surfactant and acidic surfactant. So this acidic surfactant will behave as a proton donor. So that means it will make the polarons available again at the polyaniline. So we will get back a green color solution. So that green color solution, we will filter it, wash it, and then we will add with this powders. So actually this is the part that we will add the powders. and then we will let it to get integrated. Well, we will allow it to like 12, not 12, I think 18 hours like that. And then we will filter and we will do the coating. So the coating wise, we will do a drop coating method, because drop coating is also easy. We don't have a spin coater here. So drop coating means we just use the dropper to coat it on the glass slide. So we know that we normally use the microscope glass slide, because glass slide is also cheap. So initially it's not conductive. Once we have coated by using this conducting polyaniline, it will be conductive. And then we will dry the film, and then we can use it for the sensor measurement already. Okay, here we applying the ex situ method, because if let's say I use this surfactant, because if let's say we wanted to have a processable, which means a polyaniline which is soluble, one of the major drawback of the polyaniline is it's not soluble. If let's say we do a normal procedure like this, you will end up getting polyaniline powder which is not soluble. We can just make a disperse, we can just make it disperse. But then our concern is to produce something that is processable, which is like, you know, totally in the solution form without any particles formation and so on. So that's why we actually have to add this DBSA at the initial stage itself. But if let's say we add it over here, so this is a surfactant, right? So surfactant means something like soap. During the filtration, it will be a problem where there will be a soapy kind of a thing will come out. During my PhD time, there are times that I just sit and doing this washing for like a month, maybe 1.5 months also got. When I go sub-zero temperature, like -10 degrees Celsius, yeah, I've said like, you know, for a quite long time in the lab, just do the washing every day. So I don't want that to happen because my focus was with the FYP students. They have a very limited time frame, right? So we wanted to go fast without compromising the conducting properties. So that's why we adopted this method. And yeah, we managed to get certain conductivity level as well here. Okay, then the sensor measurement setup. So this is the very first setup that we used. Okay, for a gas sensor, that was the first study that I've started here, gas sensor. So for a gas sensor, I think the ideal equipment is Keithley, because I see many literatures that report on Keithley, and there are many other instruments as well. But those are expensive, which is not affordable. So the only affordable and available thing in my lab was the multimeter, because multimeter can record the resistance changes as well. So here we focus on the resistance changes. Since it's a gas sensor, we just focus on the resistance changes. So this is a simple setup that we do where, you know, when we develop a gas sensor, so the target analyte, the target gas was ammonia gas. So we will normally heat up the ammonia at a very mild temperature so that it will form some fumes over here, the vapors, and then the vapor will get into the tube and it will go here. So the moment the vapor comes here, we can see some changes over here. The reading will start to, you know, it will fluctuate, and then it will become stable, but it will take some time. It will become stable, so we will record the timing. We will record the reading to calculate the sensitivity. Normally, gas sensor will look into the sensitivity. So, okay, that is one-way measurement. That means we just detect, and then we want to reuse. If possible, we don't want to, you know, like keep changing the glass slide, because every time we coat also there might be some minor changes as well, right? So we want to reuse the same coating. So initially what we did a redoping process. This is actually not redoping. It's like we just suck out where the one that already exposed to the ammonia gas, we use a pump to suck out the ammonia gas and also whatever is inside. So normally their attraction, it's a very physical, very loosely bound attraction, ammonia and also the polyaniline. So it will be easier for us to take it out. Which means when we apply some pressure to suck it out, so even the film also will change color back to green, and then we will resume back the resistance or the conductivity of that conducting polyaniline, and then we can reuse it back. This was true for the shells, that means the hard shells. But when we move further into the chitin or chitosan kind of a material, we find this setup didn't work for us, so we changed the setup. we changed the setup where we use aquarium pump. We insert the aquarium pump, the small, it's very cheap. I think you can buy it like two ringgit or something like that. We insert it inside the ammonia solution, or to redope we use hydrochloric acid. So here the VOC is actually ammonia. So and then we on this pump so that it will produce the fumes. So the fume will go up, the fume will go up and enter, and then it will produce a certain value over here. And then to redope, that means to flush off, we'll open the outlet, and then we will close this inlet, and then we'll open this outlet over here for this hydrochloric acid, the mild acid 1 molarity hydrochloric acid. So when the hydrochloric acid comes in, it will flush off. At the same time, the reading over here will be resumed back. I mean, the conductivity it will get back, and then we can reuse the film. So this setup worked very well when we use this chitin based material. Okay, next let's look into some of my results and discussion. So conducting polymers, especially on this polyaniline, when we study this polyaniline, there are two fingerprint technique that we actually can confirm whether our polyaniline or the composite material has formed or not. One of the thing is by looking at this values of the benzenoid and quinoid, because this is quinoid structure, this is benzenoid structure. If let's say it is in the emeraldine salt state, then you can study the area under the graph of these two peaks, and then you can try to find the ratio. I've reported that in my PhD work. So if let's say we get like kind of equal, that means the ratio is like 1 to 1. Say for example, the benzenoid is 1, quinoid is 1, then we can assume that this is in the emeraldine salt form. Okay, but then we still need to further confirm by using UV vis, because this 1 to 1 ratio is true for ES and also EB, emeraldine base. Okay, because these two structures will have equal amount of benzenoid and quinoid. But if let's say we look at the licomaraldine, then the ratio we will get more for the benzenoid. So maybe just simply write numbers over here, maybe 2 to 1. The benzenoid will be more for the licomaraldine. So this is the way that we can prove a little bit on the formation of whether we got this conducting polyaniline or not. Okay, so here we got one problem, right? Like even though we know that now, if let's say we get 1 to 1 ratio, we know that it is in the emeraldine form, but emeraldine salt or base, we can confirm by looking at the UVVs. So here there are three peaks, typical peaks. One is a pi to pi star peak, which is around 340 nanometer. And then normally, if let's say ES, then it will have this shoulder peak. It's like a characteristic peak. If let's say this is not ES, this is EB, then the graph is going to look something like this only, where we will have two peaks. One is around 340 something, another one will be around 600 something. Okay, but here we got like around 700 something, because this shows the enhanced polaronic character. I have to wipe this off. Okay. So we also checked, I mean, in terms of the, after we add with the filler, these shells, X2 addition. So what happens to the polaron side? So here the B is actually pristine polyaniline. Okay, but then here, if we look at the C and D, this is like 40%, 60% ratio of the shells. I think this like kind of too much on the surface of polyaniline, which maybe blocked I would say block the transport of electron. Normally we use the term delocalization. Maybe when it's too much, it blocked the electron movement. So it's like we don't get a good polaron absorbance over here. But then for 20%, we actually got higher. But this thing we couldn't prove by using conductivity, because later I'll show the conductivity data. Okay, so this is some of the EDX analysis. Actually, this EDX, this EDX and this EDX is the same instrument, because as time goes by, I furthered the study with a different batch of FYP students. So first we studied about the chicken eggshells, then we studied about the quail eggshell, got crab shells. So here we observe, we actually wanted to make sure that we can find the calcium or not through the EDX. So in all EDX spectra, we can find the calcium. So it has been well blended. When we look at the typical structure of this connecting polymer composites, it's a typical structure where we will get like a flaky structure for the pristine penny, or sometimes people might get like globular as well, depends on the conditions that they control and so on. And chicken eggshells, we don't see a much improvement. We can just see that there is certain degree of porosity here. Okay, where the chicken eggshells, I think maybe when inserted into the, because we use submicron size of the chicken eggshells, so maybe enter the pores of the maybe the polyaniline matrix. For the quail eggshells, actually we managed to find lots of porous nature like this. These things are good for the gas to go in, to travel, and then for the sensor measurement. And then for the crab shell, we actually found some kind of elongated structure. So this one I will come back later, because this structure actually, I couldn't relate. That time I couldn't relate. Like, how come calcium carbonates can cause polyaniline to give some elongated structure? So I will explain this again later. Okay, so this is the conductivity analysis. So this is a formula that we normally use. We will actually calculate the resistance, and then we will execute by using this formula to calculate back the conductivity. So here, this is the one that I told you. This is not directly related to the absorbance, but we can do some kind of absorbance ratio study. So where it can be related. Okay, so it's a typical scenario where pristine penny normally will have a higher conductivity compared to any of the other composites, because the fillers that we are adding in are non-conductive. So definitely it's going to suppress the conductivity, but it doesn't compromise in terms of the gas sensing measurement. So that's what we're going to see now. So since we wanted to go as simple as possible, and also we have to do it within a very short period of time, the study. So we just go for a calibration curve. So normally when we compare the calibration curve, almost in all the shells that we have used, we got the 20 milligram. The 20 milligram is the optimum one. Like, this is chicken egg shells, where we got a good linearity when we use chicken egg shells. And this one comes from the crab shells. But polyaniline we will synthesize every time. Okay, so every batch will synthesize a new polyaniline as well, because if you store it for a longer time, then it might degrade as well. Okay, so from here we choose the 20 milligram with the penny. Penny is actually the polyaniline, the short abbreviation for the polyaniline. So we further the study with other parameters to calculate the limit of detection from the calibration curve. So here we can see the threshold for the ammonia, as I mentioned earlier, is 25 ppm. So we managed to get lesser than the threshold value. So in a very simpler manner, I feel like this is good. It's showing some response after we have added, because pristine penny, it fluctuates. Every time we synthesize, sometimes we will get like 50 ppm, sometimes we get 70 ppm, the limit of detection for the pristine penny. But after we have added with the shells, it improvised. Why? Probably because these shells went in between the tangled polyaniline chain, and then it maybe make it kind of expanded. So it maybe made the electrons to move much easier, so that, the polarons, so that, because the polarons are the one which will react with the ammonia. Okay, so these are some of the other reported studies we compare. It's comparable, but there are, like, sometimes some of the material, to make the material is expensive, but here we got it like some good LOD results. In terms of other sensor performances, we cross-check with common gases. So we found almost all the time we will get a good selectivity towards ammonia, probably because of the because of the dipole-dipole attraction of the electrons between the polyaniline and also the ammonia. And reusability wise, we managed to, okay, so here, this is the way where we look into the gas sensor response and also the recovery time, but we could not report it over here. That's the thing, that's a problem actually. When we use the K3, it's like computer integrated software. So you can see a more flexible lines where you can clearly see. This one, when we use the multimeter, we have to manually measure the time taken for us to get a good results. But sometimes we have to let it to get equilibrium. The contact time we have to increase. Then we measure, yes, we will get the higher sensitivity much more easily. So here, when we on the gas, that means the target gas, the sensitivity increases, and then when we off, that means when we redope, it will come back. Right? This is not conductivity. Yeah, this is actually related to the conductivity, but here we respond in terms of the sensitivity. Okay, sensitivity, they got a formula, relative formula. So in this case, we assume if, let's say, the sensitivity drops below 90%, then it's not usable after that anymore. Right. So next, about long-term stability. So for the chicken eggshells and crab shells, we found the stability somewhere around up to 8 days. And after that, probably due to because we have to every time take it out and then we have to put back into our container and so on. So maybe there might be some humidity interaction, which causes it to lose some sensitivity. Okay, so these are the few papers that we have published by using this polyaniline with the waste shells. Like this paper we published under the Polymer Engineering and Science under the Wiley by using poly shells. So this paper, all of them are Scopus Index, but very local journal. Like we have one, yeah, this is in a local journal that we publish, the Membrane Journal we publish. So the others are international journals. So this one, this is the first study actually we conducted on the chicken eggshells. And then this one we use, I think, yeah, we use various composite materials. And this one just focused on the mussel shells as well. So next, yeah, so this is one of the paper, if let's say you're interested to study further on this, connecting polymer-based gas sensors and so on. Somewhere this year, we collaborated with my colleagues, Dr. Siti Noratika and also Dr. Ruhaida, where we publish under the Degrader publisher, Chemistry Teacher International. So it's an open access paper, anyone can access, where we introduce a basic and also very simple guideline to prepare conducting polymer or polyaniline, and also how to let it, I mean, how to apply it in the applications of photocatalysts and also gas sensor measurements. So it's a very simple paper that was published early this year. Okay, next, I would like to talk a little bit before I move further to the third part, which is chitin chitosan related. I just would like to introduce, this work done by my postgraduate student, where we developed an electrochemical sensor to detect PFAS. PFAS specifically, we detected PFOA, perfluorooctanoic acid. Nowadays, you also can find PFAS. It's one of the major concern, one of the hot topic in US at the moment, because it has been manufactured like many years ago, and then they have stopped manufacturing because of its very bad effects, notorious chemical. All right, so you can actually Google this picture, PFAS on your plate. Almost anything that we eat might contain PFAS. And in US, some studies stated that even they started to find PFOA in the rainwater at the Antarctic, Arctic. These areas also they started to find this scattered PFAS. So it's actually a concern at the moment. Okay, so the available techniques are, as usual, chromatography technique, which is really, really sensitive. But we all know that chromatography techniques are kind of, what do you call that, tedious. So we wanted to develop an electrochemical sensor. There are a few sensors on electrochemical. So later I'll show the comparison. So when we started this work, actually EPA's threshold value is 70 parts per trillion, PPT. But unfortunately, we could not achieve the PPT level due to the sensitivity challenges. We could not achieve the PPT. 70 ppt was the initial one. Then later this year, EPA announced for the PFAS 0.0, to be exact, 0.003 something at the PPT. Here I just put that then. So this is the new PPT. When they announced this new PPT, another concern raised in America where none of the existing simple sensors cannot detect this PFAS anymore already, because their PPT, even though some sensors can go like PPT level, majority of them are PPB levels. So none of them cannot use. They have to go back to the chromatography technique to detect. Okay. If you are interested about this PFOA or PFAS material, probably I would recommend you to watch this movie. One of the movie that inspired me actually. It's a very slow story movie acted by Mark Ruffalo and Anne Hathaway. But it has some scary point like what it can do to human and also to animals, to the environment. PFA. This story is solely about the PFAS. Okay, this is the first discovery. It's based on true story, so probably you all can watch it. Okay, so this is our study where we developed a polyaniline chitosan modified on screen printed carbon electrode for the electrochemical detection of perfluorooctanoic acid, which is PFOA. So in short, we don't want to use these expensive electrodes, so we just go for the SPC. It's not to say cheap, but this project was funded, so we got some money to buy these screen printed electrodes. So we developed in situ. This one this is a master's work. So we have the time, even though affected by the pandemic. So we developed an in situ based polyaniline chitosan. But this chitosan, since my topic today is about waste fillers, right? So this chitosan, actually, initially we used the crab shells. So if you can recall back, I did mention that in one of the scanning electron microscope image, it showed some elongated structure, which motivated me maybe to go and study further. And then I realized, only that point I realized, okay, this could be due to this chitosan as well, because crab shells contain chitosan material, but it's a totally different types of isolation. So we isolate chitosan. We didn't buy, we isolate the chitosan from the crab shell, we integrate it with the polyaniline, and then finally we use some TPV technique because of sensitivity and also the high resolution. So as we can see here, so it shows some good reproducibility and also reusability, because one of the concern is normally screen printed electrodes are kind of use and throw, but here we didn't throw, we can reuse it. Like maybe we can go more than 5 times as well, but here we just use it for 5 times. Even long-term stability also, we can use it like for about 3 weeks. And we compare it with some existing sensors in terms of a limit of detection, and we were like good. I mean, the sensor that we developed, limit of detection is 1.08 ppb, because when we look at the other materials, and also when we study their papers, it seems to be more expensive compared to what we have developed over here. Yeah, so that's the thing. But yeah, the problem is we could not achieve the threshold value. Okay, but still fine. We managed to detect, because this PPT is the water level. If let's say PPB, if let's say we wanted to, we are concerned about PPB, threshold value for human fluid is PPB level, threshold value for human fluids. Okay, but in the water, yeah, they become very strict. Okay, so this is the third part where I just wanted to share what are the waste-related projects that we have done. So here we used, this is not a sensor. We used a squid pan. Normally when we eat the squid, it will have a thin transparent sheet like a plastic, right? So we collected this, and then we produce, we actually wanted to produce chitosan or chitosan. I'm not sure of the pronunciation, chitosan or chitosan. But then, it takes time. So we stopped until the chitin, and then we integrated with the polyaniline, and then we try to remove chromium. But this one, we got very low yield. Few problems happen. Very low yield, which is 20%. Okay, that means out of 5 gram of chitin, only 1 gram we got. 5 gram of squid pen, we only managed to get 1 gram of chitin. Then our removal percentage also 60 to 70%. So we go back to the the traditional, the normal chitin. So the normal chitin here is we produced from the shrimp shells. So here we got higher yield. Even their degree of acetylation also is good. And then the chromium removal percentage went up to like 83 to 99% under optimized conditions. Okay, so this is about the waste shells as well, but not sensor in focus. Okay, when I further studied this topic on this chitin and chitosan, because now I'm focusing on the polyaniline and chitin chitosan based material, I came across that, oh, mushroom also actually contains certain types of mushroom, they contain. This picture is from my working review paper, so I don't have a proper data here. As you can see, some are still leave it blank. So what makes different between chitin and chitosan is that the acetyl group. So that's why normally chitin means we will refer to degree of acetylation, how much of acetyl group we have. If let's say chitosan, this acetyl group will be converted into just amine. So it's basically deacetylation. We remove the acetyl. So here we will refer to DDA, degree of deacetylation. So this is one of the mark that we use. So yeah, mushrooms also can be a source, and there are not many papers yet. But now I see, starting this year, I started to see there are many studies. Okay, there are many studies started to come, but then almost all of the studies are at the beginning stage where they just isolate the chitosan with different methods, and then there are some papers on application, but we can count. It's not like hundreds over paper like that. It's less than 100 like that, based on the review that I've done. Okay, so that's why it was interested me to work on the isolation of fungal chitin or chitosan. And in fact, we did one. So here, first of all, I just want to show a comparison. Okay, I will try to go fast. The benefit or the advantage is that we basically, for the crustacean-based chitin and chitosan, there are demineralization, deproteinization, bleaching, deacetylation. There are 4 steps. But for the fungal-based chitin, we can save time. We only have deproteinization and deacetylation because it has hard shells. And if let's say we're going to make biomaterials, then if let's say cream by using chitosan from the crustacean base, it might cause allergic. But fungal, it won't cause allergic. Okay, so this is the advantage of fungal chitin and chitosan. So here, another study that we have done by using some wild fungus, wild mushroom. We extract chitin and then we apply it by using responsive phase methodology. So we actually got, by manipulating 3 variables over here, we actually got a good, reliable model over here. Okay, so box Benken design. So we normally look in terms of the p-value and also some other error values. So from here, we also extrapolated it into studying the dual factors. So here we made loading. Sorry, due to the limited time, I could not explain further on the loading, because if let's say we are going to make a polyaniline in the solution form, the loading is important, because many papers, they just produce powder form and then they will disperse in the solvent. So that is fine. The one, they don't need to bother about the loading. Yeah, they will do the calculation, but it's like dispersion. But solution form, there is a calculation to make to find out the loading percentage. So we have studied this interaction by using box Benken design. So we actually got some promising results as well. Penny chitin for the ammonia sensor, but this chitin we extract from the wild mushroom. So as usual, when we compare in terms of this R square, we got for the penny fungal chitin, it responded a good, it shows a good linearity. And then in terms of limit of detection also, when we compare for the pristine penny, we got 70 ppm, but then for penny fungal chitin, we got 15 ppm. This is the ammonia sensor. So the selectivity was good. The reusability also, like we managed to get it up to 6 cycles. Okay, yeah, this one we only managed to get up to 6 cycles. After that, it started to deteriorate the performance. But yeah, since I had the interest on the fungal chitin, and also at that time actually the pandemic started and so on, so I started to grow mushroom, just a fun activity at my home by using sawdust. But this is nothing special, just sharing, because I think almost 90% of industry, mushroom industry in Malaysia, they are using sawdust because that is very easy to get. But now at world global level, the sawdust is depleting. So sooner or later, they might go after some other alternative sources. So that was the concern. Therefore, we proposed, this project we proposed under one of my colleagues, Dr. Sitinoratika. So we managed to get some money to conduct this project where we're going to use a new circular approach where we're going to collect this kind of domestic waste, food waste basically, and then we're going to make mushroom substrate and then going to grow. So the works are ongoing. So I don't have any progress pictures over here to show. So as for the conclusion, I think I would say that, yeah, whatever that I've presented is very simple studies because we had many limitations in terms of instruments, funding, manpower, and so on. So, but I still believe there is a potential for these shells to be a new paradigm in terms of sustainable waste management. If let's say we can bring it to the market, to the commercialization. And another opinion is that these shells, okay, basically these shells, fillers, they will definitely found their path or their way in the circular economy if let's say it finds a proper monetary values. Because like now we see metal scraps, it has a value, aluminum cans, papers, okay, because people are buying it. So same thing, if let's say we need more research on utilizing these waste materials, and if let's say we can find a proper application or proper usage, probably it can create monetary value. And after that, all this what is the restaurant name? I forgot. Okay, these restaurants which are producing huge amount of shell waste, I don't think so they will discard it. They will keep it. They will wash it and keep it because they can get some money. So yeah, that's why I feel like it needs monetary value for this waste. Then probably yeah, it will we can achieve the sustainable development goals effectively. And last conclusion is about PFAS. PFAS is one of the notorious chemical in the environment. It has been a biggest alarm in US, Australia, China, because I think they have used this for a long time. Now PFAS is no, PFOA is no more, but then they have alternatives like Gene X. The name is Gene X, and there is another one more. I forgot the name. So even though they come out with the alternative, but the effect is the same as the PFAS material. Same things. When we buy bottle products, we will look for, drinking bottle, we will look for BPA free. Fine, there is no BPA. But what industry will do is they will replace it with BPS or maybe BPB or BPAF, other analogs of these materials. So same thing happens for the PFAS. And in Malaysia also, I see during the pandemic time, I was watching Go Shop, and then I realized one of the advertisement was they promote their frying pan saying that it's PFOA free. So I was like, okay, not bad. So we have that awareness. If let's say when we look into the Malaysian studies on the PFAS material, one of the study was conducted in 2006 in Kota Kinabalu, some water area. And then in 2012, there was another study in Sungai Langat where they detected PFAS material. The PFAS they detected not at PPB level, but PPM level, which is far higher compared to the current threshold value for the PFAS. Okay, but since then, I think I saw another paper from USM lecturers where they studied, I think, PFAS from the egg yolk or something. Okay, so yeah, PFAS is a serious concern. So we can further study on that as well. All right. So that is my conclusion and some of my research interests and ongoing works. At the moment, from the gas sensor, I've slowly shifted to electrochemical sensors. And then now focusing basically on the nanochitosan, where we are trying to convert this chitosan into nanotype. The picture here, you can see Yeah, this is the normal chitosan. So this is the nano chitosan. So, but I'm not sure still the color of those films look the same or not. When we freshly prepared, yes, we can see some very good clarity here. Uh, okay, I'm not sure whether the color will retain the same or not. Yeah, so this one at the moment we are working on this nano chitosan, which we didn't buy. We extract from the crab shells, integrated with the penny, and then trying to detect the BPA. So this is this project was funded by Royal Society of Chemistry, and then we also like interested. I mean, we means my team. Okay, so the research is not possible without the team. So that's a reason. So in my team we are focusing on some edible based mushroom chitin chitosan isolation from edible mushrooms, and also optimization of this fungal chitin or chitosan from the industrial waste. So also on waste management and some design of experiments. So thank you. So this picture I normally use at the end of all my presentations, which I cherish a lot because in the beginning of my sharing session, I highlighted about three fathers of conducting polymers. So he is one of them, Prof. Alan Heger. So he's still there. I mean, this picture was taken in 2013 during my PhD time. I attended a conference in Singapore, so I met him. So yeah, so he's one of the father of conducting polymers. So with that, I think I'll finish my presentation. So thank you everyone for listening. Okay, Dr. Nick, I'm done.
All right. Thank you very much, Dr. Kavi, for enlightening us with the very interesting topic. Okay, so now I open maybe one or two questions from the audience. So if you have any questions to Dr. Kavi, you can type at the chat box or you can open your microphone. Right, Dr. Kavi, one
Yes,
question
doctor.
from me. So actually how you get the motivation to do the research from the true story and also the what we call the environment as you have done with the PFAS and relates it with the SDG 12 right now?
Okay, as I actually, my whole presentation is my whole research that I started somewhere in 2017 and up to now. So the thing is, I'm also a member of Royal Society of Chemistry. So the benefit of being a member is that every month I'll be getting a magazine. Okay, so that magazine is Chemistry World. So yeah, whenever I got free time, I will read that magazine. I'll just go through, and then there were one point. That time our team we got a FRGS grant. So we were developing this crab shell chitosan based polyaniline. At that time, I also got that. I mean, I get the chance to read something about PFAS. Until that point, I never know about PFAS. So when I studied about that, it's like okay, it sounds interesting. So why not we try to detect this PFAS by using electrochemical technique? And then I went and searched for the literature review, and at that point we found very limited. I think somewhere in 2018 or 19, there were almost no any electrochemical sensors for the PFAS. Okay, but then now I think we have several, maybe more than like 50 papers which have reported on different types of electrochemical detections. So that's where we actually started off with just chitosan, polyaniline, and that PFAS actually come in between. So when I further studied from the PFAS, I got to know about the movie, The Dark Waters. So I tried my best. I actually asked my friend to download that movie for me because that movie was from Amazon Prime or something. So I don't have that account. So I asked my friend to download, and then I watched the movies, like, getting excited because you get to watch and you get to feel that, okay, you are doing a project which is current environmental concern. So that was the motivation. It's like a process. We just went through one by one like that.
All right. Okay, so very interesting, Doctor. All right, so thank you very much, Dr. Kavi, for your presentation and the sharings of ideas and knowledge. Okay, so ladies and gentlemen, this is the end of our session. I would like to thank to all for joining us in this sharing session. So we hope that this session will be useful and beneficial to all. Till we'll meet again in the future. Stay safe and take care, everyone. Thank you. Thank you very much, Dr. Kavi, for your presentation.
Thank you, Doctor. Take care. Bye.
Okay, bye.